All right, here we go. Unit 5, Lesson 5. The intent of this lesson is just to get you one more at bat on differentiating between the intermediate and mean value theorems of calculus and how we might apply those to make conclusions about functions. So the first thing to differentiate them is the words intermediate versus mean. Intermediate, you want to just immediately think between, and mean, you want to think average. So let's first talk about the intermediate value theorem. Reading it out very specifically, the intermediate value theorem says that if a function f of x is continuous on the closed interval a to b, and f of a is less than some number y is less than f of b, so those are the outputs of your function, or f of b is less than y is less than f of a, so the other way around, then there is at least one value c on the open interval a to b such that f of c equals y. Meaning there is a value that you could plug into the function to get exactly that y value. So that sounds pretty complicated until you look at like how simple an idea it is. Literally, this is just saying if I start at point A and I finish at point B, as long as my function is continuous, so it doesn't have any jumps or holes in it, it's saying that you can't get from f of A to f of B without crossing through the line on the screen S, or any imaginary line S that we are calling the output of the function. So it's basically saying you are going to hit every single value between f of A and f of b as you travel them, as long as your function is continuous, right? Because if it wasn't continuous, you could like go along this path and then jump over the line. So that is what the intermediate value theorem tells us. Second, we have the mean value theorem. What the mean value theorem tells us, or the average value theorem, if f of x is continuous on the closed interval a to b, and differentiable on the open interval a to b. So not only does it have to be continuous, it also has to be differentiable, for reasons we'll get to in just a second. Then there is guaranteed to exist a value of c on that interval a to b such that, I'll do a couple of notations here, f prime of c, right, that's the derivative, that's the instantaneous rate of change, that's the derivative, that's the slope of the tangent line, right? The slope of the tangent line, it's saying there will be some tangent line slope that is equal to the average rate of change, or the secant line slope. And you can see visually why that has to be true by looking at this picture here. If I draw that secant line from A to B, so A comma f of A and B comma f of B, and you imagine, say that's like your speed in the car, your average speed. So say this is the miles you have gone towards your destination, and this is hours. And if I say your average speed here is 70 miles per hour, well then at least at one point between A and B, you must have been traveling exactly 70 miles an hour. In order for the mean value theorem to hold, your function both has to be continuous, same as the intermediate value theorem, but it also has to be differentiable, meaning smooth, no hard corners. The reason for that is, imagine if I drew this graph and it looked like an absolute value function, right, which only has two distinct slopes on it. Well, I could draw a secant line across the absolute value function with a slope of 0, which never occurs. Because, right, it changes instantly. So you, at that hard corner, there's no slope of 0 there. So you have to say that the function is differentiable as well. Let's see how those would be applied. And this is going to be the real nuts and the bolts of it and key points to remember. First, the justifications. To use the intermediate value theorem, you must say that the function is continuous. And on the AP exam, it's kind of silly. They'll tell you it's continuous, and then you have to say it back to them to basically say you know why you can apply the intermediate value theorem. If you're applying the mean value theorem, you have to say it's continuous and differentiable. There's a trick to both of these, and they won't tell you that it's continuous and differentiable. They'll usually just say it's differentiable because of this idea here. Differentiability implies continuity, meaning if I tell you the function is differentiable, I am also telling you that it's continuous. The basic logic there is if I tell you a function is differentiable, I'm also telling you there's no holes, right? Because we couldn't take the derivative at that jump. So if I tell you a function is differentiable, I'm also telling you that it's continuous. You'll see in a second how you actually do have to say this. You have to say that you know that differentiability implies continuity. And finally, you must explicitly state the endpoints you're using. So let's take a look at this in a table. First, we have values of x and g of x. And the prompt says, use the table below, which represents the values of a differentiable. See, I told you they would tell you a differentiable function, g, on the interval 0 to 6. Be sure to completely justify your reasoning. That means you have to apply the relevant lessons from points 1 through 4, citing appropriate theorems when necessary. First, it says estimate the value of g of 2.5. All that means is where would 2.5 fall? Well, it would fall between 2 and 3. If you don't know any points between, your best guess is just the average rate of change. So literally all this means for you to do is to say g of 2.5. This says estimate, so I'm not going to write an equal sign. I'm going to write an approximately symbol. And we're just going to have here, g of 3 minus g of 2 all over 3 minus 2. And so what we have there is g of 3, right? G of 3 is 5, minus g of 2 is 1, 5 minus 1, over 3 minus 2. So what we have here is 4 over 1. G prime of 2.5 is approximately 4 over 1. Okay, so nothing really doing there, nothing to prove. Those estimation things come up a lot, and sometimes it's just unclear what you're supposed to do. So let's look at our first actual IVT one, or MVT one, we'll see. Is there guaranteed to be a value of C such that G of C equals 1? The really important way to know whether you're going to be asked about the mean value theorem or the intermediate value theorem is to look at your table and say, am I being asked about the same function I was given, or am I being asked about one level lower, the derivative of that function? In this case, you're being asked about the original function, g of c equals -1. So we're going to be applying the intermediate value theorem. And so I don't see any actual values of g equals -1. However, I do see, right, and there's a bunch of different choices you could make here. I'll just use the full interval. If I say here, if I look at g of 0 and I look at g of 6, they're -3 and 1. And so -1 falls between those. And so here's the most succinct way to write this. Here's exactly what I would write. I would say g of 0 equals -3, g of 6 equals 1. Then I would say statement 2, g of x is differentiable, meaning it's smooth, no hard corners. And here's what I would say, therefore also continuous, because if it's differentiable, that's point number 3, really important. Differentiability implies, tells you a function is also continuous. Therefore, g of c equals -1 at least once. And this is really important. You have to give the interval on 0 to 6. Now here's the interesting part. You don't actually have to name the theorem, but I'm going to. I'm going to say by the intermediate value theorem. So recapping a few key points. Number 1, list the endpoints that you're using to apply your theorem. 2, it's kind of 2 parts here. State continuity. And in this case, since you weren't told the function is continuous, you have to say it's differentiable, therefore also continuous. And finally, restate the conclusion, basically answer their question back to them. Is there guaranteed to be a value? Yes, g of c equals -1 at least once on that interval by the intermediate value theorem. Again, this is optional, but I kind of like to write it because it helps me really think about what I'm doing. Okay, so the trickier one here. Is there guaranteed to be a value c such that g prime of c, right? So this is my derivative. This is my instantaneous rate of change. My derivative equals 2/3. And your clue that this is going to be an MVT problem is that you are not given a single value of g prime of x. You are not given a single value of it. So the only way we can prove its existence is using the mean value theorem. We need to find somewhere on this table that the average rate of change is equal to that instantaneous rate of change of 2/3. Now, most of the time when I've seen it on the AP exam, the first thing I would check is I would check the full range, and this ends up being true. So from 0 to 6, right? From 0 to 6, my change in y from -3 to 1, that's a change of 4. My change in x, that's from 0 to 6, that's 6. Yep, 4/6 is 2/3. So here is exactly what I would say. I would say the average, and you can use this abbreviation, the average rate of change of g of x on 0 to 6 equals, and I kind of like to just do this whole thing. It's worth the time to me because then if I make a mistake, I can still get partial credit. 6 minus 0. So we have here, this is, it was, what was it? G, it was 1 and -3. So 1 minus -3 over 6 minus 0. And so we would have 4/6 equals 2/3. So I've established my endpoints. Part 2, I would say g of x is differentiable therefore continuous. Have to state them both for IVT. Therefore, g prime of x equals 2/3 at least once on 0 to 6. And again, optional, but I like to write it by the mean value theorem by MVT. So that's IVT versus MVT. This will be really helpful as you go through your first summative assessment of the quarter.